Okay.
Yes, that looks good.
Can you see
so
the slides?
Go ahead. Yeah.
So I'm going to switch to the laser pointer. Okay, hello everybody, and thanks for inviting me to this workshop and giving me the opportunity to show you some new results from COMPAS, not yet amplitude analyses, but just to show you what is in our data. So this is the COMPAS experiment. It is a big hall, about 60-meter long hall. Actually, you don't see much. The beam comes from bottom left here. You don't see much except of concrete and steel. So I'm going to remove all the concrete and the steel and move to this picture here. Again, the beam comes from the bottom left. We use a pion beam, 190 GeV momentum, and then there is a target, which in our case is a liquid hydrogen target, and then we have two spectrometer magnets here that give us a wide kinematic range of final state particles that we measure. And then what will become important for the new results that I'm going to show is the calorimeters. So we have an electromagnetic calorimeter here and another one down there, because we want to include neutral particles, photons, in our final state. So this is the reaction at high S, which is typical 19 GeV, square root of S. The dominant channel is Pomeron exchange. So this is diffractive production, and we have a X particle that then decays into a multi-particle final state. And of course, the flagship channel of COMPAS has been the 3-charged pion final state, and a lot of results emerged from that. I'm going to just briefly review it. So this is the light meson spectrum, as you know, taken from the PDG and compared with a relatively recent quark model calculation. I don't want you to go into details, but just to highlight the mesons that had new PDG entries from the 3 pion charge state. So 11 new PDG entries were based on just this 3 charged pion addition. And I just want to, briefly say that there are, of course, lots of resonance parameters that were extracted. But also I want to just very briefly mention one caveat. There was this A1-1420, which was observed in the F0 pi P wave, which was classified as an exotic meson immediately because it does not really fit the expected spectrum. And here you see that it is a very clean Breit-Wigner-like peak, and also a phase motion associated with it. And we recently published, a paper where we fit the signal with a triangle amplitude, and we actually find that the triangle fits slightly better than a simple Breit-Wigner, and it has the advantage that there are no free parameters for this signal. So we conclude that the A1-1420 is actually not a new QQ bar resonance, but it is likely to be caused by a triangle from the source A1-1260 and rescattering into F0 pi. And then, well, of course, the exotic spin exotic states with 1- that were mentioned by Sean already. The PDG actually lists 2 of them, and this question has also been tackled by COMPAS in the 3-charge pion state, and here it would just show one example fit. Left is the intensity in the rho pi P wave, and right is the phase difference of the rho pi P wave to the rho pi S wave. And you see our model fits, and our conclusion is that we cannot describe the data without the 1- resonance. So the pi 1/1600 is actually needed to describe the data, and these are the parameters that we extracted. So mass at 1.6 GeV with a very wide width of 580 MeV. So the dashed curve actually shows the fit without the pi 1/1600, while the red curve is the fit, including the pi 1/1600. Now, there were some residual doubts whether our rho parameterization could actually influence this result, and that's why we very recently performed a so-called Fried isobar analysis on this particular partial wave, where we replace the fixed pi minus pi plus isobar amplitudes by model independent waves, and we do this for L equals 0, 1, and 2. There are some multimodalities that we have to correct for, but once this is done, you can show a correlation between the 3 pi invariant mass, where you see the bump actually at 1.6 GeV in this particular wave, which is supposed to be the pi 1/1600, and the dipion invariant mass, and you see there is a very clear rho in here, so at about 770 MeV, and if you make a 3 pion cut along these two lines here, so you just include events that are inside here, and then plot the 2 pion amplitude, you find the Fried isobar analysis, you find these blue data points, and you compare it with the fixed parameterization that was used in the previous analysis, and you see that it fits rather well. Also, plotting real part versus imaginary part, you see a very nice argand circle for the rho. So that basically confirms the decay of the pi 1/1600 to rho pi, independent of a given parameterization of the rho, and the results are actually consistent with those using fixed isobar parameterization. That was published in this recent PhysRevD paper here. Now, this was already partly shown by Sean. So of course, for the pi 1, it's not only the rho pi that is interesting, but also other channels. And I'm just switched to this HutSpec calculation down here, which actually in line with earlier model calculation predicts that the B1 pi is actually the dominant decay channel, and the rho pi, well, is kind of subdominant depending on the mass. So if we are at 1600 MeV for the hybrid mass, even the F1 pi should be more dominant, and then there's the eta prime pi, and even k star k bar, which is also very interesting, and the eta pi. So we are trying to extract all those additional or more dominant decay channels, and actually there's one very interesting final state, that's the 3 pion 2 photon final state, which gives us access to all these three final states. So we just select 3 charged pions plus 2 photons, and then depending on whether we make a cut on the 2 photons being a pi 0 or an eta, we can select these different decay chains. So by one event selection, basically we cover all 3 final states, and we have now a new data production with an improved shower reconstruction from the calorimeters, which improved their resolution. And we also include the full COMPASS data set for the first time. So everything that has been published up to now on these states was only about half of the full data set. And these are the invariant mass plots of pi minus, pi plus, pi 0, where you see a clear eta peak here that you can cut on. And if you have the pi minus, pi plus eta, here you see a clear eta prime peak without sitting on a very low background, and also the F1 that you can use to attack the F1 state. Now, just to remind you that it was this reduced data set that led to this extraction of the pi 1 pole, where we basically concluded together with JPAC that only one pole is needed to describe both the pi 1 1400 in eta pi and the pi 1 1600, which is dominant in eta prime pi. So I think the question of 2 pi 1s at low mass should be resolved by that. And as I said, we will add a factor of 2 data. Just to give you a glimpse, this is gives you the distribution of cosine theta Gottfried-Jackson versus the eta pi masses. So this is the eta pi channel here, and you see the A2 dominant. You can also look at the phi Treman-Young, which basically shows you that it is a clear m equals 1 production. And we now have enough statistics that we can also do a T prime binning, which we were not able to do before in the previous analysis. And this is now the new plot for the eta prime pi cos theta Gottfried-Jackson versus mass, and you see a clear forward-backward asymmetry, which comes from the interference of even and odd waves, which immediately shows that there is a exotic contribution. here. So these plots are the new ones now that replace the older ones. Let me switch to the F1 pi state. Here we can, just to get a glimpse on the kinematics, we can have a look at, just make a mask cut on the F1, knowing that it sits on a rather large background. But if you make a mask cut on this yellow region here, and then look at the Dalitz plot of pi plus eta versus pi minus eta, then you see a clear A naught, so that the dominant decay is the A naught pi. And also you can look at the same angles, theta Gottfried-Jackson and phi Triemann-Young, to see that there are also some asymmetries forward backwards, and here there's some interference between m equals 0 and m equals 1 state. So that requires an amplitude analysis to disentangle this. And again, here we can make bins in T prime. We decided to make 4 bins here, and you see that there's also, here's the F1 peak for these different T bins. Our total range is between 0.1 and 1 GeV squared. So we divide this range into 4 bins, and you see that there is some change of signal to background ratio of the F1. So that will also have to be taken into account by the fit. But then, of course, the real fit will not do a mask cut on the F1 since it sits on such large background, but it will be just performed in the full mass range, and we exclude the eta prime pi that's already seen here. So there's a very small region here which is excluded because that limits the number of waves that we have to include. And here this shows the invariant mass spectrum of the final state. So this is mx, if you so want, and this will have to be disentangled. But then, of course, there are not only F1 pi final states, but there are also other decay chains. So there's also pi plus pi minus isobars and eta pi isobars, and this is nicely seen here. And if you look in the correlation plot, so note that this is not a Dalitz plot. It's the mass pi minus pi plus versus mass pi minus eta, and you see several lines here, and that basically tells you what will be the dominant decays, which I list down here, which we will have to include in our partial wave analysis, which is about to start. Now, this state was already mentioned by Sean. This is predicted by models and by lattice QCD to be the dominant decay of a hybrid pi1 1600, and to access this requires to add 2 more photons to the final state. So now we have 3 charged pions and 4 photons, and this gives us access to B1 pi and the B1 decaying to omega pi pi. So that's the decay chain. We have omega pi pi and the omega pi, both combinations, either omega pi 0 or omega pi minus, can form the B1, and the omega decays to 3 pions. And again, we have a new data production here. We use the full COMPASS data set for this final state, which gives us about 720,000 exclusive events just in the omega mass region, which is the largest data sample worldwide, and is about 4 times more data than from the BNL E852 experiment. So this just shows some kinematic distributions. Here on the top right, you see the invariant 3 pion mass, pi minus, pi 0, pi plus, with a clear omega peak, and cutting on the mass here, we can then first of all produce the pi minus, pi 0 omega invariant mass distribution, which shows a hint of the A2 probably, and then there are other, you know, A2s and A4s sitting here. But then, of course, also the pi1 1600 is expected to show up here. But then also the pi minus, pi 0, which are not included in the omega, need to be considered as possible isobars. So here we have clear rho a peak here, and this shows the invariant mass of the pi 0 omega here, which is dominated by the B1 1235. So there's a lot to do for the partial wave analysis by including all these final states. I'm going to skip this. So that's just a glimpse of what COMPASS has in diffractive production compared to BNL. I do not compare to BlueX because that's a different production mechanism. But here you see we have about a factor of 5 at least more than what is available previously. And for the partial wave analysis, we will do, as we did for the 3 charged pions, we will do a 2D partial wave analysis in bins of mx and t prime. We want to extend the mass range up to 3.5 to 4 GeV to connect to some Regge like predictions that were done by JPAC. Of course, considering resonances in all 2-body subsystems, we are just producing our Monte Carlo samples using the Frontera supercomputer in the US. And then finally, of course, we want to do a couple channel analysis, as was done for eta pi, eta prime pi. But of course, now we have confirmed the resonant nature only of one member of this 1 minus plus multiplet, the pi 1 1600, actually the negative version of it. And we are about to extract branching fractions. But in order to confirm the hybrid nature, we need to observe other members. We need to include the ones with strangeness, and their best 3 has put observation of the eta 1 here on the archive recently. And that brings me to our new plans, which is the successor of COMPAS, which is the AMBER experiment. There was a letter of intent submitted to the CERN committees in 2018 with a long list of measurements, not only spectroscopy, but also doing Parton distribution functions of mesons. There was actually a proposal for so-called phase 1 of AMBER that was submitted and approved at the end of last year, which includes these 3 measurements using mainly a pion beam and muon beams here. And for phase 2, we are just writing the proposal now, and that will include the spectroscopy of kaons, among others, to access these hybrid states with strangeness. But of course, in order to do that, we need a high-intensity kaon beam. And the way to do that is to do an RF separation. At CERN, the beam that is sent to the COMPAS hall is a mixed beam. It is produced by shooting protons onto a production target and then just doing a momentum selection of the produced particles. There is a rather small momentum spread of about 1%, but the beam may also contain other particles. And in order to enhance the component that is due to the kaons, we actually want to kick out all the others or most of the others. And that is done by so-called our radio frequency separation, which includes 2 sets of RF cavities at a distance which is as long as possible, because you give a transverse kick to the particles here, and then there is a difference in the velocity of the particles when they have different mass, and then this transverse kick is either compensated or enhanced by the second cavity, depending on the relative phase that the particle arrives here. And this way you can dump most of the unwanted particles and put the kaons, for example, around here. Since this length here is limited to somewhat less than a kilometer due to the beamline, we need high frequency cavities, and the present design value is about 4 gigahertz. Which gives you then a quite good separation for this beam. I can show you a plot later on. So that's what we plan to do for the kaons. I mean, I think the kaon spectrum is much less known than the non-strange light meson spectrum. There are about 25 kaon states listed by the PDG, 13 of which need confirmation, and that's what COMPAS or AMBER wants to do. Of course, we have done some preparatory work. We have looked at existing data where we mostly had a pi minus beam, which has about 2.4% admixture of kaons, and we have Cherenkov detectors sitting in the beam that actually tag each incoming particle. So this is done by the CDAR detectors, so we know whether an incoming particle is a pion or a kaon, and that way we can actually select the kaons. But of course, at a much smaller statistics than we expect for AMBER. For example, we looked at these final states. So this would be the pendant to the 3 charged pions, K minus, pi minus, pi plus, which gives you access to all kaon states. We looked at K short, pi minus, and also at lambda p bar. I'm going to show you a few results of that. So that's the 3 charged particle final state. K minus.
5 minutes left.
Okay, all right, thanks. K minus, pi plus final state. You see the invariant mass distribution of the 3 particles shown on the left here, and then the invariant masses of the neutral isobars. And well, there are clear peaks which probably can be attributed to these particles here, but then of course it needs a amplitude analysis to really see the resonant structures here. So this is the world's largest data set on these states so far, with about 720,000 exclusive events, and we plan to exceed that by a factor of 5 or something like that with Amber. Now, we actually did a preliminary partial wave analysis on this final state, since basically you can just use the machinery we have for the 3 charged pions, replacing one of them with a kaon. But what we see here is that the K star pi S wave is the most dominant, with some resonances visible. But the problem that we saw is that this low mass part below about 1.5, where actually most of the statistics is actually dominated by leakage, and that is mostly due to the limited particle identification that we have for K minus in COMPASS. So that is something that clearly has to be improved. We cannot really distinguish a K minus from a pi minus at momenta larger than about 50 GeV, and that leads to a rather large leakage down here. So that will make this analysis to be taken with a grain of salt. But we do see, at least above 1.5 GeV, we see, for example, peaks in the 2 minus 0 plus K2 star pi S wave, and we see clear hints of K2s. Here we also see various structures in this wave here, which have to be analyzed with a resonance model fit to clarify the nature. A bit easier for us is, just to mention, the goal would be to collect something like 20 million exclusive events in 1 or 1.5 years, depending on how well the RF separation works. An easier final state is to look at K short pi minus, with the K short decaying into pi plus pi minus. And that's what we see at the moment. And you see 2 very clean peaks here, and you can look at angular distributions already to learn about the production and the quantum numbers here. And again, here the goal would be to just extend this by something like an order of magnitude with Amber. So this brings me to the conclusions. I think, well, everybody here would agree that the QCD and the strong coupling regime is still far from being understood. What I've focused on is the identification of exotic multiplets and the measurement of their decay patterns, which I think is mandatory to clarify that it is indeed hybrid or something else that we're looking at, as discussed before. We need large data samples for complementary production mechanisms. So that makes GluX and JLab, of course, important, because photo production is an important production mechanism, and this is also seen, for example, in the Pi 1 1600, which does not seem to be photo produced at JLab. We need advanced analysis methods, because as we've seen with the A1 1420, and that's why I just reminded you of that, simple Bright-Wigner fits may be misleading, and we need reaction models satisfying the principles of S-matrix theory. But then I think it is very timely, because there are advances in lattice QCD, which are basically, going in parallel with the data, and actually the techniques that are needed to analyze lattice data are very similar to the ones that the experiments do. And with amber, the goal would be, among many other measurements related to hadron structure and proton radius and so on, we'll perform precision spectroscopy and basically hopefully rewrite the PDG for the KJ and the KJ star states as we did for the AJ and the PiJ states. Okay, thanks a lot for your attention.
Yeah, thank you very much for this interesting presentation. Other questions? Okay, no questions so far. I have a question concerning slide 29. You mentioned that you are currently still lacking the K- PID and it's not perfectly. So is there anything planned to upgrade this for the AMBER experiment?
Yes, that's what we are starting now to do Monte Carlo studies of acceptance. So there are two ways of tackling this. I mean, one would be to lower the beam momentum. So going down from 190 GeV to smaller beam momenta, which still would have, you know, diffractive production and Pomeron exchange dominant. And on the other hand, to add what we call rich zero right after the target, which would then be able to identify, say, particles above 50 GeV. And going down in momentum may actually be needed to get a cleaner separation of the kaons from pions. So that's also, I think the current value is 70 GeV beam. That gives you about 50% kaon content in the beam. So that would help, but I still think that we would need some kaon PID above 50 GeV to cover that last piece of phase space.
Okay, thanks. Sean?
Yeah, no, thanks for this really nice talk. It's really impressive to see some of the mass spectra you have. I guess I was curious about this this 3 pi eta final state. So do you have some feeling for the complexity? Because you said that you're going to do a PWA of this full final state, if I understood correctly. And so do you have a feeling for how the complexity of that PWA compares to the complexity of the 3 pi PWA, just in terms of the number of parameters or anything like that?
Well, it will be more more difficult for sure. I mean, we will start by using. I mean, this has been done by E852 already with the smaller statistics, and we will start with their wave set and then you know, increase it step by step as we have done for the 3 pi. But it certainly is more complex because you have, you know, different isobars and in the different final states. And yeah, I mean, definitely it will be more complex, but we are just, you know, now in the process of writing down all the ways that we expect to contribute. We see if we look at the invariant mass spectra of you know, combinations of isobars, we see what should be there in any case, and then we will have to see. Yeah, but I hope that, you know, maybe by the end of the year we can show more. But it's definitely more involved than the 3 pi. I agree. Yeah.
Yeah. It's still exciting. Thank you.
Thank you. Another question from Bipla.
I had a quick question. I mean, is it possible to do other topologies? For example, K-shot 3 pi. So instead of K pi pi, add more final states, because then you would get access to K-shot pi pi. So look at the neutral K1s and so on. Is this a statistics problem? I mean, do you?
For the moment, it is statistics limited, yes. But for Amber, I mean, this will certainly be, I mean, taken into account, yes. I mean, we did look at K short pi pi already in the compass data. Nothing has been released so far. I mean, we do see lots of structure there, but we hope that with Amber this will get much better. Yeah.
I mean, in particular, do you see any isospin breaking effects between charged K and neutral K?
We're not at such a level of detail yet. I'm sorry, that I can't say.
Okay. Okay.
Okay, then thank you very much, Bernhard. And we switch to the next presentation, and it will be given by Selva Ramirez, and he will talk about the updates